So this presentation is about a little-known sutra in Bharati Krishna Tirtha's Vedic maths, which goes by the name of Antyayoreva. And this is made of two words, Antyayo and Eva. The word Eva usually means only or indeed, and the word Antyayo, the case ending is the yo on the end. There's a dual case ending. The word Antya usually means final, but can also mean the limit or the edge of something. And I will be showing, I think, 10 or 11 applications of this sutra, generally translated as only the last terms. But this word Antya does have several meanings. And I'll look at some of those. It can mean the limits of something, the edges, the outermost parts, the first and last digits or terms, the last two digits, the last terms, or the first terms. So it has all these variable meanings. And any problem in maths that comes under this sutra can be solved using one of these meanings. So the first application I'm going to look at is in arithmetic series. So we'll start with this. The mean value of an arithmetic series is half the sum of the first and the last. So let's look at this example with a series consisting of 6 terms, 5, 9, and so on through to 25. And we can find the mean by adding the first and the last and dividing by 2. So x bar is 5 plus 25 divided by 2, which is 15. We can also find the sum of the series from the mean by multiplying the number of terms by the mean. And so the sum will be, the formula for the sum is Sn is n times x bar, where n is the number of terms, in this case 6. And 6 times 15 is 90. And you can understand this from the conventional formula. So this says that the number of terms times the mean will be n over 2 times a plus l, where a is the first term and l is the last term. And the formula for the last term is a plus n minus 1d. And so you can see how this relates to the conventional formula n over 2 times 2a plus n minus 1d. The next application is for geometric series. And this can be the well-known formula for the sum of a geometric series involves Antyayoreva, and this can be seen in the formula's derivation. So if you have a look at the standard derivation of this formula, we start with a geometric series or sequence a plus ar squared up to ar to the power of n minus 1. On multiplying both sides of this equation by the ratio r, we arrive at ar plus ar squared, etc., all the way through to ar to the power of n. So that sequence has the last term and the following term. So we're going to be looking at those two terms. On subtracting the two equations, we get a telescopic effect where all the middle terms eliminate each other. And we have Sn minus r. Sn is a minus r to the power of n. And on factorizing the left-hand side and rearranging, we arrive at the conventional formula for the sum of terms in a geometric sequence. So, for example, in finding the sum of this geometric sequence, 3, 6, 12, 24, we can put in the first term in the formula as 3, and then the next term on from 24 will be 3 times 2 to the power of 4, and that gives 48. So we have 3 minus 48 over minus 1, which gives 45. The third application is very simple, indivisibility. Simple divisibility for 2, 5 and 10 rely on the last digits of a number. And likewise, divisibility by 4 uses the last 2 digits, 8 the last 3 digits, and so on. I won't dwell on that because it's too well known. Here's an application, estimation. Estimation frequently requires rounding numbers to one significant figure, and hence using only the first terms. So for example, we might have this division here, and we want to get an estimate for it. By rounding both these numbers to one significant figure, we arrive at 600,000 divided by 30,000, which is 20. The real value is 18 point something. But for an estimation, this is close enough. And related to this are the problems involving bounds or accuracy. And these involve upper and lower bounds and require the use of limits. Here's a problem as an example. A rectangle has an area of 15 square meters and length of 3 meters. Both measurements are correct to the nearest whole number. What is the maximum width of the rectangle? So we can write down that the area is sandwiched in between 14.5 and 15.5 square meters. And the length is sandwiched in between 2.5 and 3.5 meters. And the formula to obtain the width is to divide the area by the length. And if we want to find the maximum width, then we have to choose the right values out of those 4. And to get the largest number, we're going to use the maximum area divided by the minimum length, like so. So it's going to be 15.5 divided by 2.5, which is 6.2 meters. The next application is factorization. There are many cases of factorizing polynomials where inspection of first and last terms proves useful. Suppose we have to factorize this quadratic. One way is to form a matrix of 4 numbers, and in the first column shown here we put down the factors of 3, namely 1 and 3. This is particularly useful when when one of the terms, either the first term or the last term, is prime. So given that we've got an easy factor, or a relatively easy factorization here, we can use 3 and 1. Then we've got to put down in the second column factors of 14, 2 factors of 14. Well, we could choose 1 and 14 or 2 and 7. And in this case, it's going to be 2 and 7. We've got to get them the right way round. And the way to do this is to look at the sum of the cross product. So here I've put the 2 in the top row and the 7 in the bottom row, because 1 times 7 add 2 times 3, that's the sum of the cross product, gives the middle term, middle coefficient, 13. And from there we can just write down the 2 factors as 1x plus 2 and 3x plus 7. Limits of quadratic functions, the 7th application. When completing the square for a quadratic, the last term of the binomial and the last term of the expression provide the location of the minimum or maximum point. So we have a look at this example. Y is x squared minus 6x plus 16. We can complete the square by adding and subtracting 9. And the first three terms, namely x squared minus 6x plus 9, gives the square of x minus 3. So we land up with x minus 3 squared plus 7. The minimum value for y is 7, and the location is 3, 7. So we take the minus 3 in the last term of the binomial is minus 3. We change the sign to give plus 3, and that gives us the x-coordinate of the minimum value. Now, the reason for this is that the minimum value of x minus 3 squared is 0 because it's squared. If x minus 3 was negative, then squaring it would become positive. So once we've got the completing the square, we can obtain the minimum point, in this case minimum, just by looking at the last term of the binomial and the last term of the expression. Application 8, area under a curve. Here we also use limits, of course, in definite integration. So an example, find the area under the curve y is square root x between the limits of x is 4 and x is 9. So we form up the integral, integrate to give 2/3 x to the power of 3 over 2, and evaluate between the two limits 9 and 4, which gives a result of 38 over 3. Application 9, the method of differences. This gets a bit more technical here. So in this problem is to show that the sum from r is 1 up to n of 1 over r times r plus 1 is equal to n over n plus 1. Well, let's just have a look at the arithmetic here. If we were to write down the sequence of terms, the series here would be 1 over 1 times 2. That's when r is 1. When r is 2, we get 1 over 2 times 3. When r is 3, we have 1 over 3 times 4, and so on. Now, if we just have 4 terms in the sequence, we get this series here. And what the formula says is that that will be equal to n over n plus 1. And if n is 4, then the result is 4 over 4 plus 1, namely 4/5. Let's just check that out, see if it's true. Well, if we simplify these fractions, we get a half plus a sixth plus a 12th plus 1 over 20, the lowest common multiple for which is 60. And adding those fractions up, we have 30 plus 10 plus 5 plus 3, which is 48. And 48 over 60 is 4/5. So it works for n is 4. Well, to show it algebraically, the first step is to separate out this fraction 1 over r times r plus 1 using partial fractions. And the result of which is 1 over r minus 1 over r plus 1. So each term can be expressed as that. So we can write down the terms in the series as 1 over 1 minus 1 over 2. The second term is 1 over 2 minus 1 over 3. The third term is 1 over 3 minus 1 over 4, and so on. And the last term is 1 over n minus 1 over n plus 1. And you'll notice here that we have, in this series, we've got minus a half plus a half, minus a third plus a third. So we have got a telescoping situation, and all the middle terms eliminate each other. And we're just left with the first term and the last term, namely 1 minus 1 over n plus 1. And these can be added together to form one fraction, which simplifies to n over n plus 1. So this is the method of differences. Proof by induction. The formula for the sum of a series can often be proven by induction, in which the last two terms are used. Here's a fairly common example. Prove that the sum of numbers r squared from r is 1 up to r is n is 1/6 n times n plus 1 times 2n plus 1. The first step is to show that it's true for r is equal to 1, or n is equal to 1. And if we, so r squared will be 1 squared, and on the right we would have 1/6 times 1 times 2 times 3. And sure enough, that is equal to 1. 1 squared is 1. So the formula is true for n equals 1. Then we assume it's true for n equals k. So we can write the right-hand side of the formula down with n replaced with a k. And then we're going to add the next term to both sides. So the next term will be k plus 1 squared, which is added to both sides. And then we work on the right-hand side. And this simplifies, after you've done the factorizing. So you can see that k plus 1 can be pulled out as a factor initially. And then we can pull out 1/6. And finally, after a little bit of manipulation, we can see that the expression is the same as the initial expression, but with k replaced with k plus 1. So therefore, it is, if it's true for n is k, then it's also true for n is k plus 1. So here we've used the last term and then added one more term on. Last application, small angle approximations using Taylor series. This application uses Antyayoreva in the sense of the first one or two terms. So the Taylor series for cos x is 1 minus x squared over 2 plus x to the 4 over 6, and so on. And for small values of x, terms in x to the power of 4 and higher are negligible. And so the approximation is 1 minus x squared over 2. And these small angle approximations for cos theta, sine theta, and tan theta are very commonly used in engineering, engineering, physics, astronomy, and so on. So, just to summarize what we've what I've been looking at here, we've been looking at the application of this sutra to arithmetic series, geometric series, divisibility, estimation, bounds, factorization, limits of quadratic functions, area under a curve, method of differences, proof by induction, small angle approximations. And there are several other applications of this sutra, such as in the mean value theorem. So I won't go into further details of that now. But the question does arise, are there applications outside of mathematics? Because I'm sure there are problems in everyday life where we just pay attention to the edges or the limits of an object and not worry too much about the middle. Here's a nice example to finish with. A well-known paragraph written by a Cambridge student illustrates how the use of recognition of limits is a common psychological activity. Can you read this? It's very interesting that it's readable and understandable, and as he says, the words are recognized from the first and the last letters being in the right place. This doesn't always work, particularly if there are lots of double letters involved, but it's an interesting illustration. So I hope that those applications on the sutra are interesting for you, and you can see how something in this, that you can see how these sutras operate, because they each have very many sort of slightly different applications according to the flexibility of the meanings of the words in the sutra. Thank you.